Okay, thank you. Can you hear me through the microphone? Yes, good. Okay, thanks to the organizers for... Sorry. Oh. Thanks to the organizers for this wonderful workshop. And thank you for staying. And I would like to welcome the 1 million viewers that will be watching this presentation on YouTube. Salute. Well, you never know. I'll be talking about Lyman Alpha Emitters as a probe of the Epoch of Reionization in this talk, and I think it complements what we've discussed so far at this meeting. We've talked about probing the Epoch of Reionization with the 21 centimeter transition of the diffuse gas in between galaxies. We've spoken about intensity mapping of collection of galaxies, and what I'll be discussing is at least one way of detecting individual galaxies during the Epoch of Reionization. And I'll talk about why I think the Lyman Alpha line is an interesting way to look or either spectroscopically confirm the presence of these galaxies. I'll very briefly discuss the Lyman Alpha propagation through opaque media, which will be important to understand why it may very well be possible to see Lyman Alpha emitting galaxies from the very high redshift universe. Given what I've told you about what we now think is, very reasonable theoretical description of how Lyman Alpha propagates through galaxies and the intergalactic medium, I think I'll describe to you the data, which is actually quite surprising and is indicative that we are seeing into the end of reionization at redshift greater than 6. I'll discuss that in detail. The details interpretation depends, and I think especially strongly on Lyman Alpha transfer through galactic winds. And I think this is a very fundamental and very interesting problem in the study of galaxy formation in general, because it provides you with insights into the distribution of cold gas in and around galaxies, and also its kinematics. And if I have time, then I'll discuss a little bit on why I think understanding this radiative transfer through galactic winds and intergalactic medium is actually very interesting in shaping the observed clustering of Lyman Alpha emitters, even well after reionization is completed. So, we've seen this picture before, so what I'll be discussing is, the formation of the earlier galaxies when the universe just started the reionization process. I will not describe what it is. I think we've seen it before. The beginning of the universe is on the left, and there are some speculations that the end of the universe actually occurs tomorrow. So that's why I'm even more grateful that you are here on the very last day of our existence in this talk. Okay, observable properties of early galaxies. So one thing that... no, I actually don't know what you're talking about, but... Okay, so one thing we know about galaxies that formed, or what we think we know about galaxies that formed in a very young universe, is that they formed stars out of gas that was much lower in metallicity. So what we know from stellar evolution and stellar atmosphere models is that if you have stars that form out of gas that is much more metal poor, the effective temperature of these stars goes up. So what I'm plotting here is just the luminosity of a star. This is a star with a mass of 15 solar masses. This is the luminosity, so this is 10 to the 5 solar luminosities. And this is the effective temperature. So as you decrease the metallicity, the gas metallicity, you crank up the effective temperature of the star by a factor of a few. And I think what is particularly interesting is that for the mass range of tens of solar masses, you crank it up from several tens of thousands of Kelvin here, up to potentially 10 to the 5 Kelvin. And this is really interesting because the black body, black body spectrum of a 10 to the 5 Kelvin emitter basically peaks beyond the hydrogen ionization threshold. So you get, if you have these metal poor stars, they basically are much more efficient at emitting ionizing photons. Now, in practice, what this means is that these ionizing photons are effectively absorbed in the interstellar medium of these young galaxies and processed into nebular recombination lines. And we know from atomic physics that if for case B, under the assumption of case B recombination, which is reasonable in the interstellar medium of galaxies, you form about 60 to 70 0.6 to 0.7 Lyman alpha photons per recombination. And if you take into account collisional effects, you can boost this number further to order unity. So effectively, if you crank up the number of ionizing photons that you emit in metal-poor populations, you effectively also crank up nebular lines, which are dominated in flux by Lyman alpha. So this is from very recent work by Anna Reiter and Daniel Scherer and collaborators. So what is shown here is the fraction of the bolometric luminosity of a galaxy. So this is 0, 10, 20, 30, 40% as a function of gas metallicity. So this has nothing to do with dust. It's purely stellar evolution and stellar atmosphere modeling. Now what you see is for a given curve is as you go to lower metallicity, you crank up the fraction of the total luminosity in the Lyman alpha line. You can crank it up by a large fraction. Now you can imagine, so I've drawn all these different curves here, which are basically for different initial mass functions. Now you can imagine as your initial mass function is more top heavy, you give more weight to the massive stars, and those are, they're the effect of boosting the ionizing luminosity is strongest. So you can get substantial boost factors, and we don't really know what the initial mass function of these galaxies is. I mean, so it's very, it's definitely a realistic possibility that 20 to 40% of all the radiation that is emitted by these early galaxies is in the form of a single line. So, that by itself, should. Oh, and another thing I think that is interesting is if you phrase it not as a fraction of the bolometric luminosity, but just as a rest frame equivalent width. It's about 3,000 angstrom in the rest frame. So this is factor of 30 higher than, what is considered a strong Lyman alpha emitting galaxy, say at redshift 3. So, so I think, this should make you wonder about whether it's possible to, to detect this emission. I think it's, a very obvious question. I think another thing that Avi and I looked at a while ago, people argue over whether radiation pressure is important in even present-day galaxies. This is more ionizing. This is ionizing radiation, but it is. I think it is definitely a possibility, and we need to investigate this in more detail. That if all this flux comes out in the Lyman alpha line, and this Lyman alpha line can be very effectively trapped by column density of neutral hydrogen that we commonly see in galaxies. You can imagine cranking up the radiation pressure of the Lyman alpha line by a large factor. So, this may actually play a role in these high redshift galaxies. So, but I'll return to the detectability of the source. I mean, the first answer you could give is, we know that the relevant optical depth to Lyman alpha photons through a neutral intergalactic medium is tremendous. The Gunn-Peterson optical depth is about 10 to the 6 at a redshift of 10, for a fully neutral medium. Now, technically it's not true that you suppress the Lyman alpha flux by a factor e to the minus the Gunn-Peterson optical depth. In reality, you absorb the photons and they scatter around and into these very diffuse halos, and this is what Avi had shown with George Rybicki a while ago. Now, generally, the surface brightness of these halos is also way too faint to be detected. Well, by a few orders of magnitude. So the short answer appears to be no. And I kept this in just because I think this is a very nice example of a 4-point dipole. I always plan to remove this joke, but especially for the YouTube broadcast, this is to the younger viewers in the audience. Okay, Lyman alpha propagation through opaque media. So this is to, so wrong. It is not difficult. It's not impossible to see these sources, and I'll explain this now. So one thing we know about, so the Lyman alpha cross-section can be tremendous, and I've plotted here cross-section as a function of velocity offset from line center. So this is for a gas at 10 to the 4 Kelvin. So as you move in the center of the line, the cross-section can be 10 to the minus 14 square centimeters, which is 11 orders of magnitude larger than the Thomson optical cross-section. As you move away several tens of kilometers from line center, you move into the wing, and the cross-section falls off as a Gaussian, by several orders of magnitude. It's 4 or 5 orders of magnitude until you hit the Lorentzian wing, and then it falls off as a simple power law. So, this is quite essential in the Lyman alpha scattering process. So what happens So the Lyman alpha transition corresponds to the ground state transition to the 2p states. There's basically only way down, and the Einstein coefficient for the transition is very large. It's 10 to the 9 per second. So you absorb a photon, and you basically instantly, for astrophysical purposes, cascade right down to the ground state. So absorption followed by instant re-emission is just scattering. So as the photon scatters in the frame of an atom, energy is conserved. But in the lab frame, the atom will have a thermal motion. So basically you get a Doppler boost, which changes the frequency of the photon. So every time you scatter, you change the frequency. So as the photon is scattering through a medium, it changes its frequency slightly. So it turns out that this scattering process, this random walk that the photon has through an opaque medium, also corresponds to a random walk in frequency space. And as you move away, by several tens of kilometers per second from line center, all of a sudden, we know from the previous plot that the cross-section drops by 5 orders of magnitude. So your mean free path shoots up by 5 orders of magnitude. So all of a sudden, it's much easier to escape. So, you can actually analyze them. You can compute that as a result of this particular process, what the resulting spectrum is of photons that emerges from a medium that is optically thick. And that I've shown that here. So this is flux density. Again, as a function of velocity offset from line center. So in the line center, the photons have a hard time escaping. And generally what you get is this symmetric profile of photons that emerge from such an opaque medium. And the characteristic offset, the characteristic velocity offset of these peaks from line center scales with the column density of hydrogen. Now this is very well known. It's a very old solution. So, I've reproduced that particular result here. Now the interesting thing for astrophysical purposes is that if you then replace the static medium, so this is for a static opaque medium, what I was showing you before. If you replace the static medium with an expanding medium, and the net result, this is just schematically, the net result is to suppress the blue peak of the line. And that is because photons, and enhance the red peak of the line. And this is because photons that are on the blue side of the line, basically in the frame of the expanding gas, appear closer to resonance. So effectively, the escape probability goes down. At the same time, as the photons are propagating through this expanding medium, they do work on the outflowing gas and transfer some of their energy and momentum. So, just as a result of the radiation pressure, you lose some of the energy too. So there are two effects that cause you to make a line asymmetric, and in the case of outflows, bias to the red. So this is interesting because it suggests that if you can measure these profiles in detail, it gives you a handle on the medium through which the photons are scattering, which I'll get back to. So, now we can show quite easily why we think Lyman alpha emitters provide a good probe of the epoch of reionization. So what I've actually shown here, what I'm showing you first, is a simulation of reionization, or a semi-numeric simulation run by Andre Messinger. So this is a simulation with a size 250 co-moving megaparsec on the side. It corresponds to 1 or 2 degrees. And what these simulations basically show, and others as well, is that reionization occurs very inhomogeneously. So you have these expanding, these H2 bubbles that expand. They're centered on, the regions where galaxies are clustered. And the expansion of these clusters is driven by clusters of galaxies, or not clusters of galaxies, but galaxies that are clustered. So, okay. Now this is very important for the visibility of Lyman alpha emitting galaxies. So here I've just schematically drawn this, a representation of this inhomogeneous reionization scenario. And if you have a galaxy that happens to reside in one of these large H2 regions and it's emitting its strong Lyman alpha line, as the photon is propagating through the expanding expanding universe, it actually redshifts away from resonance. And as I showed you before, a few tens of kilometers per second is enough to already reduce the cross-section by, by 5 orders of magnitude. But if you have a sufficiently large H2 bubble, you can actually redshift away by hundreds of kilometers per second, in which case you are far enough away from line center that you have a finite probability of actually making it to the observer. So, on the other hand, if you are a source sitting in a medium which has a very small H2 bubble or nothing at all, then you basically scatter and start scattering and undergo this random walk in real and frequency space until there's basically, these photons are not destroyed but end up as a very diffuse halo that cannot be probed by existing facilities, and even not for facilities that are planned for the future, at least not directly. Okay, so it is interesting. So this is basically, if you have these H2 bubbles already, you boost the visibility, the potential visibility of these Lyman alpha lines if they are emitted by these galaxies. Now you can get a head start obtaining such a redshift through phenomena that we see in basically all galaxies at redshift less than 6. So if we look at galaxies at redshift less than 6, we see that they're often surrounded by outflowing material, cold outflowing material. So I've drawn here a schematic picture of a galaxy. The observer is sitting here, the eye. This is the galaxy. And what we see is low ionization metal absorption lines that are moving towards the observer. So the redshift of these absorption lines is lower than that of the galaxy. So we know it's in between us and the observer, and it's coming towards us. On the other hand, if we look, and that is actually shown here. So what I'm showing here is the distribution of the median low ionization metal absorption line, the offset from the systemic velocity of the galaxy that is inferred from, say, a nebular line such as H alpha. So you can see that the median velocity offset is about 160 kilometers per second to the blue. So, most of these galaxies have this outflowing material, almost all. On the other hand, if you look at the Lyman Alpha emission line, you see completely different behavior. The line is always redshifted, or almost always redshifted, with a median redshift of like 500 kilometers per second. And this is related to what I was telling you about these scattering through an expanding medium. You systematically redshift the line away. From resonance simply through expansion, through scattering through this expanding medium. So that is shown here. So, and what the interesting thing is that some people, some groups have actually used very simple representations of these galactic winds. Have a simple shell of neutral hydrogen gas that is expanding around your source of Lyman alpha photons, and you follow the propagation of these photons through these winds. And it turns out that you can actually reproduce fairly well the observed shapes of Lyman alpha emission lines in galaxies all the way out to redshift 6. So that doesn't mean that this model is physically correct, but there is something interesting in these models that is approximating reality. So this is something that there is obviously debate about, because how can this possibly be real? It is not realistic, so how can it work? But I'm not going into that in this talk. But the interesting thing is, so what I've shown you before is that I was saying you need a large H2 region to render the radiation visible. But now you have the galactic winds, and these galactic winds do not even need to be large scale. They can be kiloparsec scale. They can be the size of, smaller than the size of the galaxy. It's a pure radiative transfer effect. You basically can you already start with a redshift of several hundreds of kilometers per second, and this doesn't even require very large. It doesn't require hundreds of kilometers per second in outflow velocity. So, both effects. So I think inhomogeneous reionization is a reasonable. I think would be considered very mainstream. Galactic winds are considered very mainstream in the Lyman alpha transfer community. So I think when you just combine these simple two ideas, it becomes very hard. It actually becomes more and more easy to detect Lyman alpha emission even through completely neutral media. So what I'm showing here is I'm quantifying that statement. So I'm plotting here the fraction, the probability distribution of the transmitted fraction of photons through the IGM, which is now 90% neutral by volume. So this is the very early stages of this really is early during the epoch of reionization. So here is the transmitted fraction, 1%, 10%, 100%. And what I'm showing here is the distribution for, the first picture that I was showing you. You just have galaxies sitting in these large H2 bubbles. Because these galaxies preferentially populate these ionized regions, they're even without having any winds, this blue dotted line, there's still a small fraction of the galaxies for which you transmit more than 10% of your photons, even though strictly speaking the Gunn-Peterson optical depth is very large. Now what I've done is taken one of these spherical shell models with a hydrogen column density of 10 to the 20 and an outflow velocity of 25 kilometers per second. And you get a tremendous boost in the fraction of galaxies for which we see more than 10% of the radiation. So, and then what you can do is, what I've plotted also is if you crank up the velocity to 200 kilometers per second. And the reason this particular parameter combination is basically the median of what we see, of what people infer for galaxies at redshifts less than 6. So, this is, I guess, representative of something at lower redshifts. But even for low expansion velocity, the effect is really there, and it's quite strong. So what I'm showing here is exactly the same. So we have some nice interactive talk. We have 2 people watching YouTube live. Excellent. So I'm trying to focus. Okay. So this is the same plot, but then for a neutral fraction of 80 by volume. So you see that there is now actually the inhomogeneity of this reionization process is kicking in quite a lot. You can see that it's actually a majority of galaxies, even for the low wind velocity, you can transmit more than 10%. And the reason, I don't know if you remember this, but the reason I said I think 10% is already an interesting number is that if it's true that you can get an intrinsic rest frame equivalent width of 3,000 angstroms, then getting a transmitted fraction through the intergalactic medium of only 10% still gives you an observed rest frame equivalent width of 300, which is still considered very, very strong, and it's among the highest that would be observed today. So what I've just shown you in this previous plot is that it's possible to transmit more than 10% of your flux, your Lyman alpha flux, even when the universe was 90% ionized by hydrogen. Or another way of saying this is that the effective optical depth to this radiation was less than 2. Now, the Gunn-Peterson optical depth that I just showed you is more like 10 to the 5, 10 to the 6. So, this is obviously something that plays a very important role in the detectability of these galaxies. So, okay, so just to summarize, I think, so it's easier in these models, inhomogeneous reionization models, to detect Lyman alpha emission. I think the other thing that it implies is that there is an effect of the intergalactic medium on the visibility and the distribution of Lyman alpha emitting sources. But it's probably more subtle than what you guessed in, if reionization was, say, an instant event where where it would be very difficult to see these galaxies beyond some redshift. It's more subtle than that. So that's why I think the observations are actually perhaps even more puzzling, because it seems to suggest something, well, opposite to what you might expect. And that is that, okay, so let me first show you the data at redshifts less than 6. So this is, what I'm showing here is observed number density of Lyman alpha emitting galaxies. So these are selected on the basis of a Lyman alpha line as a function of redshift. So this is redshift 3, this is redshift 6. So this is luminosity, number density. The blue points are from Uchi et al. This is Subaru 8-meter telescope on Hawaii. 8-meter telescope. So these are their inferred number counts. The blue data points and the blue line is a best fit Schechter function. Now, in this particular plot, these are the redshift 6, or more accurately 5.7 Lyman alpha emitters. I've also plotted exactly the same Schechter function here, this blue line here. Right? It's actually coincident almost exactly with the best fit Schechter function for the redshift 6 data. So, this basically is saying that the redshift evolution of Lyman alpha emitters between redshift 3 and 6 is basically constant. And this has been known for a long time, but now the statistical significance is greater. Now that's interesting, because if you then go one step higher in redshift, this is the redshift 6 data again, or redshift 5.7. Now what I'm showing in red is the data at redshift 6.5. Again, from the Subaru telescope. This data is actually quite old. There is better data already, but it's confirming this picture. So what I'm plotting here, the red is the luminosity function at redshift 6.5. There are 2 sets of curves. These are basically galaxies that are only photometrically detected. The triangles are ones that have spectroscopic follow-up, and they basically, this is only a subset of galaxies of this, that were photometrically detected, basically. So this, you can view this as a lower limit on the number counts at redshift 6.5, and this is the upper limit. So there is evolution between redshift 5.7 and 6.5. I think more striking, even at the same time, is that if you look at pick the same galaxies and measure their UV continuum, non-ionizing UV continuum, so this radiation should not suffer from any attenuation in the intergalactic medium, then you don't see this difference. So what I'm showing here is the number density of galaxies as a function of UV continuum luminosity, so non-ionizing, in blue at redshift 5.7, and in red at 6.5. So unlike the Lyman alpha luminosity function, there's no evolution in the UV luminosity function. So whatever is doing this, it's only affecting the Lyman alpha photon. So hydrogen is a very plausible candidate, neutral hydrogen. So, if you want to quantify this, and the data has gotten better, what this implies is that you see roughly 30%, or for every Lyman alpha photon that you see at redshift 5.7, you only see 0.7 at redshift 6.5 per UV continuum photon. So this basically tells you that the opacity is going up by 30% between 5.7 and 6.5. So it's interesting, what that is. Okay, another way. This is not only in Lyman alpha selected galaxies. If we look at Lyman break galaxies, these are galaxies that are selected on their broadband colors. They have candidate galaxies, then they do spectroscopic follow-up and try to compute what fraction of these dropout galaxies have strong Lyman alpha emission. So in this case, stronger than 75 angstrom. And what you see is that the fraction of galaxies that has a strong Lyman alpha line is going up with redshift, between redshift 4 and 6. Statistically, it's not very significant, but you see this trend. And then at redshift 7, if you extrapolate this trend, you would have expected to see some galaxies in emission, but they don't. They don't see any. They don't have any detections of Lyman alpha in these galaxies. And this is from a paper by Dan Stark and Richard Ellis and collaborators. I mean, okay, this is one paper, but actually, there is another European group that actually found exactly the same. This was with an even pretty small sample of galaxies, redshift 7 dropout galaxies, and no detection of Lyman alpha. So this appears to be, this drop appears to be real and significant, although not in this plot, not yet. And obviously, I think the interesting point is that, null detections are very useful for us and for theory. So, right. Okay, so this is what I just told you. So the Lyman alpha selected galaxies really suggest that we see 30% less Lyman alpha flux from redshift 6.5 than from 5.7. And interestingly, the dropout population also shows that it appears harder to see Lyman alpha photons from galaxies at redshift greater than 6 than galaxies less than 6. So this is exactly what you expect, for, say, if there's a reionization related signature. And what we've done actually, I don't know, these plots that I showed you where I computed the transmission, the probability distribution for the transmitted fraction of Lyman alpha photons through the intergalactic medium. If you apply these models and you say, okay, let's for the moment say, take the best fit values of the observations. Let's not worry about their uncertainties yet. If you take their best fit observed values and try to model it, you really require the volume average neutral fraction to increase by 0.5, basically, from 0 to 50% over a redshift interval of 1, which is actually faster than what theory predicts. But I think that just emphasizes that in our current understanding, this is a very intriguing observation, I think. So, obviously, so the models, in particular the wind models that I'm using, are calibrated based on galaxies that we see at redshift less than 6. So, we don't really know how outflows behave at redshift, greater than 6. So this is obviously something that plays an important role. But I think it is, just emphasizing that this is one of the, if we want to worry about the detectability of these galaxies, then this is, I think, one of the main processes that we need to worry about. So I think this is a very, this particular problem actually plagues, plagues is the wrong word, affects interpretations of Lyman alpha emitting galaxies at all redshifts. And I think it's a very interesting one because, as I was saying before, it ties in closely with the distribution of cold gas in and around galaxies. And I think there have been some very interesting observations recently that really allow us to time down these models better. So how much time do I have, Jonathan? 12 minutes? Okay, well then I'll just mention this. So just to make the connection with hydrogen cosmology, I mean, there is a probe underway to use these Lyman alpha emitting galaxies to do cosmology. So this HETDEX survey with the HET telescope is being built by the University of Austin, Texas. Well, it has been built. So what they're doing, what they aim to do is observe 0.8 million Lyman alpha emitting galaxies between redshift 1.9 and 3.5, and use these galaxies for which we have the Lyman alpha emission line, so for which we have very good spectroscopic information. So we have a very a good tracer of the underlying density field, and if you have a very good 3D tracer of the underlying density field, you can constrain cosmology. And in particular, one of the goals of this experiment is to do dark energy. So one of the things that was interesting to me is that this transfer problem is actually, this Lyman alpha transfer problem is actually quite important for a measurement like this, and very interesting. So just to give you a very simple background, so we think even post-reionization, the intergalactic medium is a source of opacity to Lyman alpha flux. And that is because if you are a photon that is on the, on the blue side of the Lyman alpha line, so this is basically Lyman alpha, this represents the Lyman alpha resonance. If you are a photon that is more energetic, eventually it will redshift into the resonance. And we know from observations of the Lyman alpha forest that the intergalactic medium at redshift 2, 3, and 4 is not transparent to these at these particular wavelengths. So there is a finite probability to suppress the flux on the blue side of the line, while the red side of the line is all being transmitted. So now this is interesting because it suggests the fact that you have this this source of opacity suggests that implies that there is actually a density-dependent source of opacity in the intergalactic medium. That is because we know that the Gunn-Peterson optical depth scales as density squared, 1 over the photoionization rate, and then there's a velocity term here. So you can imagine. So you can imagine that if you have the sensitivity, so if the opacity becomes dependent on density, you can imagine that if you are a galaxy that is sitting in a more dense region of our universe, it's actually harder to see because the gas is more opaque to the Lyman alpha photons. So this basically acts exactly opposite to the standard bias in cosmology, because it suggests that it's actually harder. It's harder to see Lyman alpha from galaxies at redshifts, at these redshifts residing in overdense regions. And as these galaxies are selected, so these galaxies are selected on the basis of their Lyman alpha flux, you effectively reduce the number of galaxies that you select in the survey in overdense regions. So it exactly counteracts the standard bias. Now, another thing that I think is interesting is, I'm going to skip the photoionization rate. Another interesting thing is that the velocity gradient comes in the denominator. So basically, at fixed number density, if you crank up the velocity gradient, you basically smear out the same number of atoms over a larger range of velocities. So per unit velocity or per frequency, the opacity goes down. So that's interesting because then it suggests that if you are in a region where the line of sight velocity of the gas that is sitting in front of your galaxy is higher or lower, that again reduces or increases the number of galaxies that you may be able to see from such a region. Now this is exactly so this introduces, in theory, this introduces all sorts of modifications to the power spectrum of these Lyman alpha selected galaxies. And this is an effect that has been pointed out. Have I mentioned them? Yes. So this is an effect that had been pointed out first by Zhang, HETDEX, and others. So you can really these radiative transfer effects that modify the that occur on very small scales and pretty close to the galaxies can really modify the overall the clustering of galaxies on very large scales. So I've just shown one example of the spherically averaged power spectrum here, and the main point of this plot is that if you just put in a given real galaxy power spectrum, suppose you can measure this with infinite accuracy, that's given here, then actually these radiative transfer effects can strongly modify it. Now this is an exaggerated case, but I think it illustrates it, just to illustrate it. So the reason I find this very interesting is that this particular what we call non-gravitational clustering signature really depends on how galactic winds affect your scattering. And the reason is that I'm saying that the opacity of the gas is going down on the blue side, and it's basically unchanged on the red side of the line. But what galactic winds do is transfer your line from the line center to the red. So if galactic winds are very prominently present in these galaxies, then all the flux comes out here, where it's completely insensitive to whatever is happening on this side. On the other hand, if galactic winds are not that prevalently present and say, still allow you to transmit 30% of your flux on the blue side, then you are all of a sudden sensitive to this mechanism. So, what we actually concluded, which is, I think, interesting, is that, the overall amplitude of this non-gravitational signature depends quite strongly on, how you treat the galactic winds. But you can turn it around, actually. So you can say that, if you are measuring this galaxy power spectrum using this 0.8 million galaxies, you try to do cosmology with it, what you actually get for free is these parameters here that actually tell you how the Lyman alpha optical depth changes as a function of overdensity in the universe, which is, I think gives you completely independent and new constraints on how exactly this transfer process occurs in galaxies. And I think importantly, what we've actually shown with Stuart White, or what Stuart calculated, is that even the fact that we have these 3 additional parameters that we don't really know very well, it doesn't degrade the cosmological constraints too much. I mean, it affects them, but it's really not, it's not a killer for this project at all. So, yeah, I'm just going to put up my conclusions. So what I've told you is that tens of % of the bolometric luminosity of star-forming galaxies can be in the form of Lyman alpha line emission. For that reason, I think it's important to think about the detectability of these galaxies. So this may give us the only way, or like a very good way, of finding and or confirming the existence of galaxies at this epoch directly. So Lyman alpha emitting galaxies probe the epoch of the ionization state of the intergalactic medium. I think especially through the evolution in the number density, as I was showing you before. And also what is very interesting is to observe or study their angular clustering on the sky, because you can imagine, which has Matt McQuinn has shown, that the bubble distribution can modulate the angular power spectrum of these Lyman alpha selected galaxies, especially if you're well into the reionization regime. So, for this you need somewhat larger sample of galaxies, but this is a very promising way, I think, as well. So, if you look at the existing data, so it's still plagued by uncertainties, clearly, but there is an indication that we see evidence for rapid, and not like, rapid, actually tens of percent, going from completely ionized to maybe tens of percent neutral by volume, from redshift 5.7 to 7 or something like that. I think it's a serious possibility. So I've told you that in detail, if you really want to put hard numbers on this, I think at this stage it's a bit difficult because we don't understand how exactly Lyman alpha propagates through these galactic winds. But I think, this is actually something that we're working really hard on, and there's a lot of interesting data coming out, and yeah, I'll stop there. Thank you. Right.
It would be nice to have larger numbers for clustering.
Right.
Say a little about the prospects, how that stuff will increase.
Oh well, yeah. So you have the Subaru Hyper Supreme Cam. It will give you a field of view that's going to be several square degrees. I don't know the exact numbers, and I don't know actually the exact time scale of that either. But I think this will give you, if you have hundreds of galaxies at redshift 6.5, will give you a much better measurement of the clustering. But I think also, just the number counts, if you combine this clustering measurement, I guess, with, say, number counts as a function of Lyman alpha luminosity, as a function of UV continuum luminosity, if you combine all these together, I think that actually gives you a pretty powerful probe. So, yeah. Right. Right. Yes. Yes.
And if 20–40% of flux comes to Lyman alpha, a substantial fraction, then you might see an effect that expands.
Yeah.
As the Lyman alpha line shifts, then will be
yeah.
reaching. So it will be whether there is any way of varying the geometry.
Right. So I guess, yeah. So I guess the problem with, especially the highest redshift one, you only have one detection on the longwards of the Lyman alpha resonance. So yeah, this would actually give rise to some very peculiar broadband color. So you would have a very bright continuum flux in one filter, and it would then basically not be there in the redder filter. So I guess it would be extremely blue in yeah, that's right. Right. I mean, one interesting thing is that, so they found one of these candidate redshifts, 8 to 10 galaxies, they followed up and they actually found it to have a very strong Lyman alpha emission line. Like above, it was 100 to 200 angstroms. Now the only, so that was actually one of the reasons we also did this study, because we were wondering, I mean, the line was so strong that even though I'm telling you that, like when the galaxies are pristine, they have intrinsically very strong Lyman alpha emission lines. Now suppose that, redshift 8 or so, do we really expect these galaxies, these luminous galaxies, to be pristine? We don't know. I think it's probably not. But now what we were wondering is, like, what conditions do you actually need to see this? Is it really possible to put any constraints on, say, the neutral fraction and intergalactic medium, having this very strong Lyman alpha emission, and, say, abandoning the assumption that this is a pristine galaxy, say? And, it turns out it's very difficult. You can actually see this even if the universe is 90% neutral. As I showed you before, it's not so hard. But the funny thing about that particular galaxy is that the Lyman alpha line is so strong. Actually, if you compute what the broadband color should have been, it's not actually consistent with the original data, the original way it was selected. So, yeah.
Mark, about extrapolating the wind velocities.
Right.
So we have good measurements of massive galaxies that we're measuring.
Right.
What we're talking about is time is pretty typical galaxies. Well, maybe not, but maybe potentially intrusive. So
Right.
does it seem like it seems like it's possible that the wind velocity could scale with the circular.
Yes.
And then in that case, it seems like there would be no issue with like the wind reionization, where like you really need to shift the line by several hundred kilometers a second.
Right, but you shift the line by several hundred kilometers per second, even with wind velocities of 25 kilometers per second. I mean, so I was showing these results, with wind. This curve, for example, has a wind velocity of only 25 kilometers per second. So the fact that you have, this is 25. So there is an effect for low wind velocities. Now, one reason, for the Lyman alpha galaxies that we see at redshift 6, I mean, it's true that they, there will be more luminous than the ones that, for example, the one that is seen at redshift 8.6, or that may be seen at redshift 6, 8.6. It's actually not that particular galaxy, I guess, because it's in the Hubble ultra deep field, is actually not that much more luminous, right? So it's actually, in terms of UV luminosity, it's not even an extrapolation. It's in the range of observed UV luminosities for Lyman alpha emitters. And if you go to, say, the sensitivity of JWST, say, you actually need galaxies to form stars at a rate of 1 solar mass per year, basically, in order to render it detectable in any of the bands. So, 1 solar mass per year is basically the sensitivity limit that we have to Lyman alpha emitting galaxies at redshift 4, 5 with Subaru. So in that sense, again, it's not really in terms of UV luminosity, and it's not really an extrapolation. I mean, so the dust properties may be very different, right? So, I mean, that takes away, say, the radiation pressure mechanism that is acting on the dust. But I think if you take away the dust, then the Lyman alpha radiation itself may become more efficient at exerting pressure on the gas. So there's, I think there's a lot of interesting questions there.